And we are live. Okay. Hello, everyone. My name is Jonas Nyawe. I'll be your host today for the KmerAI talks. And sorry for starting late. I know we should have started a long time ago. But so today, our guest is Irené. Uh, Good evening, Irené. How are you?
I'm doing good. It's good to see you, Jonas.
Yeah. So the way this go, I will just present you quickly or our guest, and then you will do your presentation. And at the end, those who are in the live, if people come along in the live, they will ask their question or in the comment section, and then at the end of the presentation, I will show some of uh, the question, and then you can answer at the end.
Sounds
So, yeah, good. Yeah, so it's my absolute pleasure to present Irené today for this talk. So Irené Tematelewo, if I pronounce it well, is a data scientist at Microsoft, where he works with the Bing team to develop data-driven solutions that enhance search and user experience. He is also involved with uh, TAHMO, which is the Trans-African Hydro-Meteorological Observatory Weather Network, where he designs, deploys, and monitors quality control (QC) AI systems to promptly detect malfunctioning weather sensors, ensuring the accuracy and reliability of the collected data. Irené holds a PhD in computer science from Oregon State University and a Master of Engineering from Ecole Nationale Supérieure Polytechnique de Yaoundé. Proud people. His doctoral research, supervised by Professor Tom Dietrich, focused uh, on integrated anomaly and novelty detection systems for identifying multiple types of anomalies. So today he will be presenting on improving precipitation sensor reliability. So yeah, you have the floor. Rene. Thank you for coming.
Merci, merci, Jonas. It's my pleasure to be giving this talk. It's part of the work I did during my PhD, and today's work is going to be on detecting faulty precipitation sensors. And the agenda of this talk is going to be the following. I'll start with an introduction where I will motivate the work that I'll be sharing. Then I'll discuss the different methods that we are analyzing in this work to solve that problem. Then I'll share the results and I'll conclude with a brief conclusion on what the future work for this project looks like. And without further ado, I'll start. So predicting weather is critical in so many aspects of our lives, such as safety and disaster preparedness. So our ability to predict the amount of rainfall that we expect to see on even another major application of predicting rain is water resource management.
Hello, Irene.
Can you hear me?
Yeah, you were for the past when soon after you started, it started breaking, and if you don't
Let me
mind,
switch to my wife. Can you hear me?
yeah, I can hear you clearly now.
All right. So yeah, I was saying that our ability to predict weather is critical in safety applications such as our ability to flood and so on. So the amount of rainfall we predict in a given time can allow us to know whether there could be risk of flooding and so on. Another application is water resource management. So drinking water and water for irrigation on a given time frame depends on how much rain we anticipate, so we can know if the water that are saved in reservoir are going to be enough to supply, water for drinking. Another application is climate research. So our ability to accurately collect data over time allow us to know and even to say that climate is changing, like we often hear, or that the globe is warming. So it's critical for us to be able to actually have that data over time, so we can, anticipate and mitigate those conditions. Another big application of weather forecasting, rainfall prediction, is agriculture. So, for example, more than 95% of the cultivated land in sub-Saharan Africa relies on rainfall for irrigation. And this is 90% in Latin America and 60% in South Asia. So it's therefore really critical for us to accurately predict that the amount of rain we expect to see, so farmers can plan for when to plant crops, when to harvest them, or when not to, depending on the weather pattern and the precipitation expected. And one of the issues is, like, despite the fact that right now Africa relies, or sub-Saharan Africa relies mostly on rainfall for agriculture, for irrigation, it's the continent that has the worst weather infrastructure in the world. So what this map is showing us is the distribution of weather sensor coverage in the world, and the highlighted part here is showing us Africa. So what we can see is that besides except for like this for South Africa at the very bottom of the map here, the entirety of Africa is really poorly covered. Major problem. Can you hear me? Can you hear me?
Oh, sorry. We lost you when you were talking about South Africa. Like you were.
Yeah, Unfortunately, I have to say, unfortunately, we have like a power outage in Washington due to windstorm. So I'm using my phone as a hotspot for internet. So that's why it's cutting off. Oh, but I'll keep going.
Yeah.
Okay, so I was saying that except for South Africa, the African continent is really poorly covered in terms of weather sensor, and but there are initiatives such as the TAHMO, the Trans-African Hydro-Meteorological Observatory Network, that have been started to attempt to solve this issue. So TAHMO is as an NGO, an NGO that has for goal to build more than 20,000 weather stations across the entirety across the entire African continent. And right now, we have about 1,000 weather stations. And this is the distribution of those sensors that the weather stations that we have right now. So the goal is to cover the entire continent with stations like you see right here. And those weather sensors are devices like the one we have here on the right side of the screen, which are, this electronic device contains like several sensors, including precipitation sensor, air temperature, relative humidity, solar radiation, and so on. So we deployed those to cover an entire array of field to measure, the precipitation and, all those weather variables over time. And for us in TAHMO, the most important variable right now is rainfall, for the reasons that I outlined before, like including agriculture and so on. But one of the problems with the precipitation sensor is that they often get blocked. So the device looks something like this, where at the top of the device, you have this cone or this funnel that kind of like collects water when it's raining. And that water passes through this orifice in the middle, or this orifice that you see here in the middle. As the drips of water passes through, the orifice there and falling inside the device, there's a drip counter that estimates the amount of rain that was collected. But the problem is that sometimes this orifice can be blocked, like the picture we see here on the right side of the screen. And when that happens, the sensor will underestimate the amount of rainfall that actually fell in the region where the sensor is installed. And sometimes even in the worst case, the sensor can be completely blocked, where it is reporting completely zero rainfall, including in days where you have heavy rain. So our goal is to be able to detect those faulty sensors And some of the problems or the challenges we have with precipitation or rainfall is that it's a very intermittent variable. So we've seen, events where it would rain like for say like 5 minutes, and after that it's completely sunny, and immediately, maybe it start raining again like 30 minutes away, 30 minutes right after. So you don't have the smooth variable here that you're modeling. So the nature of of precipitation is very intermittent. Another issue is that there's a low spatial autocorrelation between the stations. So if you have two stations that are even close or not, that are far away, you don't have that smooth nature where you expect to see precipitation propagate across the field in a uniform way, uniform and smooth way that you can easily model. Another issue is that precipitation is very non-Gaussian. So we all like the bell-shaped curve where, because of their, closed form property and, easy to interpret nature. So precipitation is non-Gaussian. So the picture we see here, the histogram that we see here shows the distribution of precipitation across one of our stations over 1 year. So what the histogram is showing is the horizontal axis is showing the amount of rainfall that was collected, and the vertical axis is showing the count of the day that amount of rainfall was observed. So what we are saying here is that over 365 days, more than 330 days, the amount of rainfall that was collected in this location, at this location, was 0 millimeter, which means most of the day we don't expect to see rain at all. But this is a big problem, because if you remember when I said when the sensor is blocked or not working correctly, the value that it reports is 0 as well. So usually in anomaly detection, we assume that the outliers is the rare event, or the anomaly is the rare event. But in this case, the anomaly that we expect to see is the value that is most likely. And that's a major problem, because, when you make the assumption that the anomaly is rare, then you can use like the tail of the distribution, or, to be able to detect the anomalies. But in this case, we have to find other methods. And so what is concretely the problem that we are trying to solve? So we have a network like the one you see on the screen right here, with, let's say, 17 weather stations installed at different locations. Those weather stations are reporting the data, or are collecting the data every day. And then our goal is to be able to, based on the data that the different stations reported, to be able to label or flag the ones that are not working correctly. So we want to be able to identify the stations whose measurements are not reliable, so we can send a technician to field, a technician on the field to fix the sensor or to completely replace the device. And to this end, we are comparing 4 different methods, and they are statistical machine learning methods. And we want to compare them on 3 different requirements. So first, we are looking for methods that do not need any auxiliary data. So because, one of the ways to forecast weather is to using radar, like, using radar data to estimate the amount of rainfall. But in this case, we are working with ground data, and we don't have access, or we assume we don't have access to auxiliary data like radar data that can be used as a reference to compare with the value that the sensors reported for anomaly. And the second is that we want methods that are data efficient. So if you remember, I said that in TAHMO, we currently have about 1,000 weather stations, and our goal is to get to 20,000. So we are deploying stations on a continuous basis. So we want the method that are able to work without having to wait for a long time to collect historical data. So we want methods that are data efficient. And next, we want methods that are robust to missing data or missing neighbors. And the reason being that right now in TAHMO, we've observed that on a typical day, we can have up to 50% of the stations not reporting data at all, for multiple reasons, including telecommunication issues, because we rely on telecommunication networks to send the data that are collected by the sensors back to a database for storage. And as you can see here, we are dealing with a very small number of data samples, and we want to be able to do anomaly detection with those. So deep learning methods are really out of the equation here by virtue of the size of the data we're dealing with. And the first method that we are comparing is a very simple approach. It's called the FZ filter by DeVos et al. In 2019. And what the FZ filter says is that since we are trying to detect blocked precipitation sensors, if a sensor is reporting precipitation on a given day, then it cannot be blocked. So for example, if we are trying to diagnose this sensor S1 here on the right side of the screen. So what the FZ filter says is that on a given day, if that sensor is reporting any precipitation at all, then that's a proof that the sensor cannot be blocked. And that's if rain is greater than 0, then the sensor cannot be said to be blocked. However, if the sensor do not observe any precipitation at all, then we have a second check, which is we compute the median of the neighbor of that particular sensor. So that is, okay, the sensor did not report any rainfall today. Now we're asking the question, was it a rainy day or was it a dry day? Because if it was a rainy day and the sensor do not have any precipitation, then that's evidence that the sensor might probably be broken. But if it was a dry day, then that's perfectly fine that the sensor does not report any precipitation at all. So if the neighbors, the median of the neighbors is greater than 0, then we'll say that the sensor is faulty, and then we will raise a flag. So what you're seeing here is that we're saying if we have 365 days of for the 365 days of the year, suppose this is like Monday, Tuesday, Wednesday, the 3rd, and so on. So if on Wednesday the 3rd, the condition was violated where it was a dry day, but the sensor did not report any precipitation, then we have a flag. So any of the days that this condition is so violated, then we have flags, and we can also decide that when that happens, let's say 2 times in a row, then we'll declare that that sensor is broken and send a technician to repair it. So that's the principle of this method, the FZ filter. The second one is a kernel regression that takes a different approach. The kernel regression method says that I can estimate the amount of rainfall I expect at a given location based on how much rainfall was observed overall in the network. So what it does is that I compute the amount of rainfall I expect to see at this sensor location S1 as the weighted average of the rainfall
We lost Irené for somewhere.
Can you hear me? Am I back, Jonas? I know I got cut. Can you
Yeah,
hear us?
but when you were saying explaining the weighted.
Okay, yeah. So what I was saying, I'm really sorry for the internet issue
No
today.
worries.
So what I was saying is that the kernel regression method uses a different approach. It says that I can predict the amount of rainfall using the weighted average of all of the stations' precipitation in the network. But because I know that the correlation between one station and the other depends on the distance between them, now what we do here is that we'll use the inverse distance between each neighbor and the target station to kind of give an importance weight to the voice of that station, so to speak, in the weighted average. So basically here, the weight is computed using this function, which is the RBF kernel, or the squared exponential kernel, with the parameter sigma squared and L squared. So what we're saying is that if the difference between the value that was reported by the sensor and the prediction is bigger than a certain threshold tau, then we will say that the sensor is faulty, and we will raise a flag, just like in the case of the FZ filter. Otherwise, we assume that the sensor is working. And the third method is a joint Gaussian. Even though we found that the distribution of precipitation is non-Gaussian, by doing transformations such as the log transformation of the raw precipitation, then we have a distribution that looks a lot more like a Gaussian. So here, what we do is that we apply a log transformation over the precipitation recorded over the entire network on historical data, and then we model the whole thing as a joint Gaussian after log transformation. And now what we're saying is, like, if I want to know what is the amount of rainfall I expect to see at the sensor location S1, then I can take the conditional distribution condition on the rest of the stations. And which is why this formula right here on the top left corner of the screen is telling us that the amount of rainfall I expect to see at sensor location I can be computed as the mean of the conditional distribution given the rest of the neighbor or the rest of the stations. And the beauty with the Gaussian is that it also comes with a measure of uncertainty given by the variance, that the conditional variance that we have here. And with that, just like in the case of the kernel regression, we can compare the square difference. We can use the square difference between the observation and the prediction. And when that is bigger than a certain threshold tau, then we will declare that the station is faulty. And the beauty with the Gaussian, like I was saying, is that it comes with a measure of uncertainty given by this by the variance of the conditional variance. So here, what the conditional variance is giving us is that if I have the prediction, if the difference between the prediction and the observation is big, but with a high uncertainty, then I don't want to penalize the station for that. So that's what essentially dividing by the variance here account for reducing the false alarm when we have a low uncertainty on our high uncertainty on our prediction. Finally, the fourth method that we're comparing is a method that we currently have deployed in the TAHMO weather network, which is essentially a mixture of two models, a logistic regression model and a linear regression model. So what that method essentially is asking is like, okay, we want to detect the sensors that are not working correctly. So the first thing we do is let's predict whether we expect to see precipitation on a given day or not. So this P of R greater than 0 given the neighbors is just what is the probability of seeing rain on this particular day at this particular location. And along with that, we also have the prediction of the amount of precipitation we expect to see. And then with that, we can compute the probability of seeing the amount of rain that was observed at this mixture model, where if the reported precipitation was 0, then we know that that probability can just be 1 minus the probability of seeing precipitation. So the probability of having 0 precipitation is just 1 minus the logistic regression model's prediction here. But if the precipitation reported by the sensor was greater than 0, then we have this conditional model instead, which is the weighted density using the mean of the linear regression that we had to parameterize this Gaussian multiplied by the probability of rain itself. And the principle is the same as before, but here we use with this probability, we can use a method like the negative log probability as an anomaly score. So if you have a high probability that the amount of precipitation was what we were expecting by this model, then you will have a log of 1, which will give you a score of 0, and then you won't raise any alarm. On the other hand, if the probability is close to 0, then this negative log will give you close to infinity or a large number, which is a sign that there probably is an anomaly on that particular station. So these are the 3 methods. And one thing I want you to observe is that the first 3 methods that I shared you are using a structure like this, where we are looking at the entire network when making prediction at one particular sensor location. But this model here, the conditional mixture model, is more localized. So it's mostly looking at the closest neighbor when making its prediction. And we compared the 4 methods using 2 data sets. The first one is collected from the Oklahoma Mesonet network in the US. The data was collected in the years 2008 and 2009. And then we used the data from 81 weather stations. And this is the distribution of those stations across the state of Oklahoma. And one thing I want you to notice here is that the stations are very, uniform, almost uniformly distributed across the network and very dense. The other network that we use is the TAHMO, the data set from TAHMO, where we only use the data from the region from Kenya, from a small region in Kenya. Here we use 23 weather stations collected in the years 2020 and 2021. Note the staggering difference between the 2 networks, where here we have the stations that are mostly clustered around a specific region of country, and the distance between some stations being really, really big. So along with the 2 networks, we also have explored how the data set from the 2 different countries look like. And here is the distribution. So what we're showing here on the screen is the distribution of the data set from Oklahoma and Kenya. So the first 2 plots that you see right here at the top are the data from Oklahoma. What the horizontal axis is showing us are the days of the year. So this is 1 year of data at the 81 stations across Oklahoma. So the vertical axis are the stations, and the horizontal axis are the days. And the color coding here is showing you the amount of rainfall that was observed at that particular location on that particular day. And the two plots at the bottom are the data from Kenya, where along the same principle we have on the vertical axis the days, and the horizontal axis the 23 stations in Kenya. So there's a big difference in the distribution of the two data sets. So here in Oklahoma, you can see those vertical lines that clearly show up in the distribution. Those are the days where there was precipitation across the entire network. So almost all the stations in the network reported precipitation on those days where you see vertical lines. But we have like almost none of that in the Kenyan data set, which means that the Kenyan data set we're using right here has more drier days than the Oklahoma. And also one staggering difference is also here, where we see that around this period right here from the probably 130 all the way to 300 and probably 30 also, we have like almost a completely dry period. And this is huge, because our ability to detect when the sensor is not working correctly depend on the amount of rain or depend on there being observed rain. So how do we evaluate this model? So we go from a clean data set. So we go from clean data set in which we add synthetic anomaly to simulate the behavior of a faulty or blocked rain gauge. So in this example, suppose here's an example where the plot that we have here on the top is the precipitation collected at one of our stations, in this case, Hugo. So what we do is we perform an intervention where we select a day at random, and then from that day on, we replace the observed precipitation by 0. And the reason is because when a sensor is blocked, it reports 0 precipitation. So this is a simulation of a behavior of a blocked precipitation sensor. So, and we want the models to be able to detect those synthetic anomalies that we've added. Yeah, we use 3 metrics to be able to assess the performance of each of those models. The first one is the detection delay, and the second is the false alarm rate, and the last one is the missed alarm rate. So the detection delay essentially is like how long does it take a model to detect the anomaly from the day it was added. And the false alarm rate is like what is the proportion of the false that the model, the proportion of the station that the model said were faulty when they actually were working. And the missed alarm rate is what is the proportion of the stations that the model failed to detect. So, for example, suppose that this is a weather station in which we added anomalies. So, suppose that these are the different days of the year, and that we added anomalies starting on this at this period of T star here. So, if one of the models that we're evaluating detects an anomaly during this period here on the green region, then that's a false alarm, because the anomaly doesn't start until T star, and during that period before T star, the sensor was working correctly. So this is going to be a false alarm. But if the method raises an alarm in the red region, which is this part here, then that's a true alarm. In that case, we measure the detection delay, which is the time that, the time between the onset of anomaly and the moment the model, and the date of the model raises an alarm. And finally, if the model doesn't raise an alarm at all, if the model never finds anything wrong with that station, when in fact there was anomaly, then that's a missed alarm. On the other hand, if you have a station that is working correctly, if the model raises any alarm at any point in time, we consider that to be a false alarm because there's no fault. However, if the model never raises an alarm, that's a true negative. So for each of the stations in the network, we compute this detection delay or false alarm or true alarm, and then along with that, we output what the 3 metrics that I mentioned, that I talked about: the average detection delay, the false alarm rate, and the missed alarm rate. And what are the results of this experiment? So basically, we evaluate the 4 methods I just talked about on 3 different settings. And the first one is the robustness to varying proportion of faulty stations. So what we mean by that is how does those method works when there's, for example, 5% of the stations in the network have anomaly, or 10% and 15% and so on. And the second axis of comparison is the distance, the robustness to distant neighbor. So what we're saying is, how does the method work if the closest neighbor to the target station is, say, 5 kilometers away or 10 kilometers away, and so on. And finally, we investigate the methods when the anomalies happen within the same region, or the sensor within a single region become faulty simultaneously. And for the first experiment, this is the result that we're having. So what you're seeing here on the screen is the experiment when we add, say, 5% of the faults in the data, 10%, 20%, and so on. And this is the Oklahoma data set. So what this is showing you is the detection delay, the average detection delay that it took each of the model to detect 95% of the station, the broken station that we added. So for example, if we add faults into 10 stations across the network, what we reach to detect 95% of those. Can you hear me? Can you hear me, Jonas? Can you guys hear me?
Yeah. No, when you were starting to explain the example, it cut a little bit, like to explain the score on the example. Yeah.
Okay. Yeah. So anyway, Okay. So I was saying that if, for example, we add anomalies into 10 stations in the network, so here what we are reporting is the average time that it took each of the model to detect 95% of those anomalies that we added. And then here we are reporting the detection delay in terms of number of days. So here what we can see here is that all the methods are doing, relatively well, except for the FZ filter that has like 50 days on average to detect all the anomalies, 95% of the anomalies that were added. And here the conditional mixture model, when there's only 5% of the faults added, is doing best, although not very different than the kernel regression and the Gaussian model. And here the bold face is showing the best performance, and the underscore is showing the second best. And and here is the result for the Kenyan data. And the Kenyan data, on the other hand, is like one difference we can see from the Oklahoma data and the Kenyan data is that the detection delay in Kenya seems on average bigger than in Oklahoma. So here we can, the FZ filter is detecting the anomalies in about 10 days. But here in the Kenya, the average is like it's 20 days to be able to detect the anomaly, or 95% of the anomalies. And we believe that part of the reason why this is happening is because of both the nature of the Kenyan network and the fact that the stations are very clustered across the region, with certain of the neighbors being very distant, and also the fact that the data in general was much drier and had less rainy event to allow for timely detection of the anomalies. And then in the second experiment, we evaluate the model's ability to detect faults when the neighbors are far away. So if I am in a region where I don't have any neighbors around me within like 5 kilometers or 10 kilometers, how does each of the methods' performance change based on that constraint? So here what we see is that the conditional mixture model, again, the conditional mixture model was the model that was relying only on a very small subset of neighbors, of stations around it to perform anomaly detection, is doing the best across the board. And one other pattern we see is that as the distance increased between the station and the neighbors, so does the average detection time taken to detect the station in Oklahoma. So when the distance, when the closest, when we don't have any constraint on the distance with the neighbor, we see the average being 27 days. When the closest neighbor is 5 kilometers away, we see that it takes on average 46 days and 74 days when we go to 10 kilometers and so on. But this, beyond 15 kilometers, the delay doesn't change that much. And some of the stations don't have prediction at all, like the FZ filter. This is because we are requiring the model to achieve 95% of the detection, and in this case, the FZ filter apparently is not able to do that. And again, in the Kenyan data, we see almost the same kind of pattern, where the conditional mixture model seems to also be the best method, which is the model that relies solely on the local neighborhood around the station. The final experiments we did was to investigate when the anomalies happen within the same neighborhood. So for example, what we're saying here is that what is the ability of the models to detect anomalies when the faults are clustered in the same region? So you have a group of stations that are all neighbors of each other and are not working simultaneously at the same time. How does the model handle that? And then we differentiate two cases. The case where the cluster of faults happen inside the network, where they are surrounded by working stations, and the case where it's at the periphery of the network. So essentially, in theory, or at least our expectation is that if the cluster of station is surrounded by stations that are working correctly, then there's more signal for the different method to draw from to be able to identify that these guys are not working correctly. On the other hand, when it's at the periphery, there's no station around here at the top here, for example, which gives much less signal than in the case where the stations are inside. So we investigate those two cases for the two data set or the two networks as well. And here's the result on the Oklahoma data set when the cluster contained only 2 stations, 3 stations. So here what we're saying is like, what if the number of broken stations that are clustered have a size of 2? Like 2 stations that are broken are clustered together. What if it's a cluster of size 3, 4, 5, and so on? What if have a big region of like say 8 stations that become broken or malfunction simultaneously at the same time? So what we're seeing here is that the conditional, and the in here means that the faults are happening inside, like I showed on the map, and out for the faults that happens at the periphery of the network. So what we are seeing here is that for the cluster size in, the conditional mixture model that was the winning method for the experiments I shared before is still doing well until we get to a cluster size 6. So when the cluster size become bigger than 5, then the conditional mixture model breaks apart, and then the Gaussian model and the kernel regression start to become the best performing algorithms. And if you remember, what I said is that the conditional mixture model uses local information around the neighbor to perform detection, when the kernel regression and the Gaussian models are looking at the entire network. So what we can see here is that for detecting cluster faults, drawing information from far away is useful to provide signal, compared to the conditional mixture model that only has access to local information. And as the number of stations around the target station become larger, then there's no signal to draw from to be able to perform detection. And the same thing is true in the cluster size out, except that the detection delay. Except that the detection delay for the conditional mixture model, seems to be not as consistent for the four cluster size 2 to 5, like in this case. But the story is more or less the same, that after the cluster size 5, the conditional mixture model breaks apart, and the models that draw from the signal from the entire network start working best. And here is, the first quadrant is showing when we require the model to achieve less than 20% false alarm rate and 10% false alarm rate, but the story is more is the same. So here is the result in Kenya, where here it's almost the same story, that when the cluster size is smaller than 2, then the conditional mixture model is the best performing algorithm. But as the cluster size become greater than for cluster size 4 and 5, then the kernel regression and the Gaussian models are the best method to choose from or to use. And for the cluster size out, almost no algorithm is working well because of the structure of the network. When you require the cluster to be out at the periphery of the network, then there's no station around it to provide signal for detection. And that was the last experiment. And in conclusion, so we've seen that the distribution of the stations in the network, along with the distribution of the precipitation itself, is very important when choosing what algorithm to deploy for detecting faulty stations. And we've also seen that when you have a network that is more or less uniformly, where the stations are more or less uniformly distributed, you want to have models that draw information from the local neighborhood, like the conditional mixture model that we have seen. But if you expect the station to have cluster of faults that may happen in the case of maybe a storm or something like that, in that case, methods that draw signal from far away or from all of the stations in the network, like the Gaussian model or the kernel regression, are the go-to methods. And for the future work in this study that I just showed you, we are currently investigating not only the average delay that I showed you, but also looking at the distribution of the delay itself, because the average can be very skewed by a few outliers. So you're investigating maybe some of the methods that are leading poor performance are actually having a distribution that has a concentration of points with low detection delay with just a few outliers. Another experiment we're doing is to explore the joint reasoning. So far, all of the methods are making the assumption that the neighbors are working correctly when doing their diagnosis. But we have seen that there's a possibility that one or more of the neighbors that are, being used to perform diagnosis can be faulty themselves. So we're investigating the possibility of a joint reasoning algorithm that takes into account not only the status of the station being investigated, but the neighbors as well. And finally, we are exploring the possibility of combining the different algorithms into an ensemble, because we've seen that they have different strengths in different settings. So it'd be nice to explore the possibility of leveraging the strength of that to build a QC quality control model that is more robust. And with that, I would like to acknowledge my collaborator and Austin Kaburia from Dedan Kimathi University of Technology in Kenya, and Michael Slater from Oregon State University, Dr. Shira Mena from Dedan Kimathi as well, and my advisor, Professor Thomas Dietterich from Oregon State University. And with that, I'm happy to answer any questions you have.
Thank you. Thank you so much for the presentation. So I see there are a few people online, 3 or 4 people. So if you are online and you have some questions, you can just post them right now. Then Irené can answer. And so maybe while waiting, I'll just start on my side. So I was just maybe before we joined, start with the machine learning part. I was just wondering if there is, maybe you already explained that, but there is a difficulty to make beta sensor. Are these already the best sensor, or like before like trying to do this fault setting, do we is it expensive to get beta sensor or to have some kind of protection for the sensors? I don't know if it sounds naive or something.
No, that's it. That's a perfectly valid question, and thank you. It makes a lot of sense. It's one of the issues that we actually have in TAHMO, right? So yeah, you actually touched to something that we're actually addressing, because TAHMO is basically using low quality weather sensor, because it's both cheap, and then we can have a lot of those. And given the magnitude of TAHMO and the fact that it's an probably non-for-profit, it's a non-for-profit organization. So we do use relatively cheap weather sensors. But the networks like Oklahoma that I introduced the data from in my talk, are using more advanced weather stations. But the problem that we are trying to address is not necessarily because of the sensor we are using is low quality. The anomalies that we're talking about happen because of interference due to things like debris around the station, or like when the storm from wind or something will blow objects that will block the orifice of the sensor. So it's not necessarily because of the quality of the sensor itself. It's like anomalies that happen because of environmental factors. And I was presenting once at the workshop, and then some expert from HP mentioned the fact that maybe there's an opportunity here for building automated cleaning system into the sensor itself. Like you might think of something that kind of constantly check the orifice of the sensor, and if it's blocked, then maybe automatically blow maybe some air, or some cleaning mechanism that happens automatically. But one of the issues that we're seeing right now on TAHMO, I don't know if it's a limiting factor, because obviously I did not work on the device side of the project itself, but one of the main issues that we have in TAHMO is the fact that some of the weather sensors will run out of battery, because they are battery powered. And then if you have to have something that draws power constantly to check the sensor as well, that probably won't help. That will just drain the battery as well, over time. But I believe that is definitely a question worth investigating, because what that person I was talking to was saying is that they had the same issue with, I think it was HP printers, where the ink, the head of that kind of like, releases the ink would and get like obstructed or blocked, and the sensor would just start malfunctioning. But I believe he said they found a way to kind of add another layer of security, another layer of protection that kind of like checks the ink release system or something like that.
Okay, yeah, makes total sense. Um, yeah, so then I'll yeah, so some say they missed most of the they weren't at the beginning, but yeah. So I was wondering about the data set, like I mean the data collection. I was wondering at which frequency you had this R of T. Wanted to know how at which frequency does the sensor report? Is it real time? Oh, I mean, real time doesn't mean anything, but at which frequency is like the reporting?
Oh yeah. That's a very good question. So most of the sensor we have in TAHMO right now have a reporting frequency of 5 minutes. I mean, they collect the data every 5 minutes, but we don't upload the data collected every 5 minutes, but uploaded once a day. So you imagine you have, some kind of like small database built into this device to collect those data, but only upload them into the remote database only once a day. So, and some of the sensor work, most of the sensor are like 5 minutes, but we also have a handful of them that operate at a 15 minutes resolution. So, yeah. But yeah,
Okay.
and the issue with the reason why I said we only have 365 data point is because at the 5 minutes, if you're modeling a sensor like precipitation, 5 minutes data point won't be informative for you at all, because 5 minutes is like, maybe it's raining here right now, but it hasn't started raining somewhere, nearby until 5 minutes later. Until 5 minutes later, can you still hear me?
Yeah, I can hear you.
Okay, yeah, until 5 minutes later. So usually we found that the best performance we get for precipitation is by aggregating the 5 minutes data point into daily precipitation. So so imagine we sum up the 5 minutes precipitation observed to get a kind of like a daily estimate of what was the amount of rainfall at a given location, and with that we have a stronger signal to perform any quality control.
Yeah, that brings me to my next question about this. I was wondering, then how do you deal with, since you aggregate during the day, how do you deal with those, like imagine that the sensor was working in the morning and then get obstructed, um, or maybe it was obstructed and maybe by the detection you send someone that cleaned it maybe early in the morning and then after it started working. So I'm wondering, how do you uh, how do you like make sense of this variations, like because I imagine at the end of the day you have to, because for instance for some methods, maybe I'm stuck on the first method where you had to check if there was a rain here at some point.
Yeah.
But if having a rain at some point in the morning, for instance, and then it get clocked, those is not really necessarily an indication that maybe it was valid or something. So how do you check this kind of maybe corner cases or something like that?
Yeah, no, very good question. So basically, we are operating on a daily basis. So what we mean by was it a rainy day or a dry day is based on the daily precipitation. So we are not reasoning about the individual, values in between. And again, we have other kind of rule based checks that operate on a 5 minutes basis. So, for example, here in this talk, I was discussing mostly the case where the sensor is completely blocked. But that's not the only kind of anomaly that we see with the precipitation sensors. In some cases, you will have like a sensor that report, let's say, 2 meters of rain in 5 minutes. Like that, the amount of rain that was observed was like, say, 2 meters, for example, in 5 minutes. That's completely ridiculous. And that can happen when you have, for example, maybe how do you call it? When you have like some water that stocked onto the drip count, stop on the drip counter, and the water being stuck there will make the count continually keep counting, because of a single, how do you call it? A single drop of water, keep counting like, so many times. And then at the end of the day, the device is thinking that there was 2 meters of rain that happened in 5 minutes, which is completely, historically impossible at the moment. So yeah, and so we have like other simple rules that we start our check with before we get to the point where we have to run the statistical machine learning algorithms to detect more subtle faults. But we are not reasoning about the 5 minutes point. We're reasoning about the aggregate. So what we're saying is that, does the daily precipitation reported by the neighbors suggest that it was a working day or not the 5 minutes, report.
Okay. Then when you were presenting, like for the KR, the KR
Kind of regression, right?
the KR regression, I realized there is some sigma there. So how do you set that sigma, or is it a choice?
Oh yeah, so like I said, we are working with 2 data sets. One is used to train or to estimate the parameters of the model, and the other one is used to for testing, right? So you can imagine theta and L. That was sigma and L for the length scale parameter of the RBF kernel. So we used the training data to estimate that, to estimate the best parameter that gives the best performance, the parameter that gives the best performance.
Okay. Yeah. Then the FZ formula. It's good you've talked at the end about how the status of the neighbors, because it seems. I was wondering if that because it was the worst performing, right? And is it? I wanted to confirm if it's really because of the fact that it asked a neighbor, somehow it's based on neighbors, and neighbors asked itself. There's some interdependency between,
I
or
think
what?
one thing I probably didn't do a good job at explaining is that we are basically evaluating those methods in the most constrained cases. So we are looking at really at the best performing regime. So basically the result I showed is like when we ask how long does it take for a model to detect 95% of the anomalies with less than 20% false alarm rate. So how do I detect 95% of all the anomalies with less than 20% false alarm rate? So the reason why the MZ filter we're not doing that well in some cases did not have like any entries in the table at all, but just because it's not meeting that requirement. And again, and the cases where it has like it had like a very high detection delay, we believe it's because right now in this study we are looking at all of the neighbors to make prediction, right? So you might imagine if for the FZ filter it is worth probably looking at just a local neighborhood, because when you look at all the neighbors to detect whether it was rainy at one location or not, then you're basically including a lot of noise into your estimate of a rainy day or a dry day, right? You might think that if it's raining, let's say 100 kilometers away, that does not suggest anything about, that suggests very less about the probability of raining at your location where you are. But at the moment in our implementation, which is something we're right now experimenting with, using a very small set of neighbors for estimating the median in the FZ filter, like I showed, we suspect that we'll have like way better result. But in principle, it's the method that normally is supposed to be outperforming all of the other methods.
Really?
Yeah.
Oh.
And another thing with the FZ filter, just before you jump, is the FZ filter is the only method that only asks the question, was there precipitation at all? So it doesn't reason about the magnitude of the rain that was observed at all. The only question that the FZ filter is asking is, were there rainfall or not? The other method are predicting the amount of rainfall that is expected to be seen on a given day, and use that the difference between the prediction and the observation as an anomaly score. But the FZ filter is not concerned with the magnitude at all. It's only asking, was it a rainy day or was it a dry day, and how much precipitation, did I see precipitation or not, and using that as a signal.
All right. Okay. Had a question, but I see there's a first question online, so I will take it first. Naomi ask one question: Can your work inform us about flooding, as this is a serious problem sometimes in many countries? She said she arrived late, so she didn't follow a bit the beginning. But
thank you, Naomi, for the question. That's a very good question. But my work is like at the is like kind of like the basis of being able to predict flooding, right? So my work is how do I give people enough, I mean, good quality data that they can use to build that model that in turn can be used to predict flooding, right? So I'm right at the basis. I work at the sensor level. I work at ensuring that the data that we are collecting for building those models is accurate enough that they will give us like reliable predictions later. So my research is like, okay, I have these sensors. I know that they have problems sometimes. If we leave those problems into the data set that we give to the scientists to be able to build those models that allow them to make prediction, then the prediction is most likely not going to be accurate. So I'm working really at the sensor level here. But yeah, to answer the question, broadly, yes, it can help in that case, but that's not the focus of my work. I work mostly to provide clean data and ensuring that the people that do flooding prediction can have a reliable data to build their models, especially ground data specifically. I don't know if I answered the question.
Yeah, I think so. I think so. It's like you are working at the level where, like, when, for instance, when there are not enough sensors, either let's not do anything because we don't have enough data, or we have faulty, or we can use these algorithms to like get it more cleaner data
Right.
to work with. Yeah. So yeah.
Yeah.
Yeah. Another question: what are metrics you use to evaluate the reliability of the data?
Oh, that's a very good question. I'll go back to my slide and explain that again. Give me 1 second. So basically, what we use as a metric to evaluate the quality of the data, I mean, ultimately what we are saying is that we are making the assumption that if a sensor is working correctly, then the data should be reliable. So we want to detect the sensors that are not working correctly so we can clean them, and in turn ensuring that the data that we're gathering is reliable. And then for our purpose, what we're using as a metric is the delay between the moment the anomalies was added. In this setting, we are working mostly in a scientific, setting where we have a control over the amount of faults that we added and when the faults started, and then we know exactly, because again, we are the ones adding the anomalies. So I will start explaining from here. So basically, we have clean data set like here, and then what we are doing is we are adding anomalies starting on a random day. So here, for example, we started on day, let's say 125, and then we added anomalies from there on all the way, from there on, we added anomaly there from there on all the way to the end of the year. So we know when the anomaly was added, and now we evaluate the model's ability to detect exactly when that day happened. But when the model is not able to detect, exactly the day where the anomaly started, the metric that we use after that is first the false alarm. So if you have a model that raises or that says that the anomaly started here, when in fact it started here on the T star, one of the metric that we use is the false alarm, because this is clearly a false alarm. If you say that there was an anomaly here when in fact the sensor was still working correctly at that time, then that's an alarm that is raised. If you were to send a technician every time the model raises an alarm, then they will go there and find that the sensor was working correctly, which can be very expensive if you have to do that all the time. And then, but if the model is telling you that there was an anomaly here, that's a true detection. In that case, the metric we use is the delay. Like how long did it take the model to detect this anomaly from the moment it was added? We know that the anomaly was added here on T star, and then if it's detected here on day T, so what we are measuring is like how long did it take this model to detect it? And if the model never detect that there was an anomaly in this station, if it fails, then that's a missed alarm. So what we're using as metric is this detection delay, the false alarm rate, and the missed alarm rate. I hope that answers your question.
Yeah. Futse, if you have follow-up question, ask before I go to Naomi, who had follow-up questions about her previous question that I didn't see. Okay. While Futse reacts, I will go to the Naomi's follow-up. So she was saying, because she asked, okay, maybe let me come back to Futse, because she said, but how do you conclude about the previous question on the reliability? how do you conclude about the reliability of the
data.
of the data?
Yeah, I would say that, as a scientist, again, the best we can do is to.
Yeah, she said, are there thresholds, something like that? I don't know if.
Oh, I mean, I feel like, yeah, the reliability of the data we have depends on the quality of the sensors again. And, the fewer you have broken sensors, the more reliable your data is going to be. So basically, we do our best to, how do you call it? We do our best really to have, as many working sensors as possible. But on the practical front right now, in TAHMO, we do a comparison between the data that we collect and the satellite data, but it just happened every 3 months. And if you have to wait every 3 months before you do that comparison, in between you're collecting a lot of non-reliable data. So these models that we're using here are making prediction on a daily basis, but every 3 months, a human makes a comparison between the data that was collected by the sensors and the satellite data. So that's another way I feel like we are ensuring that our data is reliable.
So maybe yeah, for say you can ask additional question. Maybe yeah, okay, she says I see. Maybe for context also is that you are. It's also helpful to these detections are also helpful because you can send someone to correct the sensor.
Yeah. So the purpose of making this daily prediction is because whenever we are convinced that, based on our model, whenever we are convinced that a station is broken or is not working correctly, then a technician is sent to go and fix it. And again, we are dealing with like African countries and villages and so on. So sometimes it can be very difficult for, or not that straightforward to send somebody to go and check it, because those sensors are basically installed in every sort of location, including like schools, like forest and things like that. And sometimes it will take, once you open a ticket to send a technician to go and check a station, it can take up to a week before that happens. And it can also be very expensive. You might imagine somebody traveling, 20 kilometers to go and check a station. And if the person goes, then it's economically costly. So we want to minimize those false alarms. That's why we have a strong requirement that our model have a low false alarm, because in principle, every alarm that the model raises is subject to investigation, and those investigations are costly if it was a false alarm.
Yeah, sure. The follow-up question from Naomi's previous question is that, do you start with these ship sensors and then you work on recalibrating, correcting the data?
The fact that the sensor is cheap doesn't mean it's not reporting accurate data. It's just that when you have more expensive sensors, then you have less problems that happen that are not related to like the data collected itself. Like, for example, right now with the sensors we are working with, like I said, we have issues with battery, where the battery of the sensor dries out really quick, and the sensor will stop working because there's no energy. But the more expensive sensors have a more backup mechanism and robust system that allow your network to operate smoothly over a longer period of time, and have like other kinds of redundancy. In Oklahoma, for example, they have I believe they have redundant sensors at every station. So let's say you are at a station like Ecole Polytechnique Yaoundé, where there's a weather station, they will have two sensors there instead of one, just for redundancy. And then when you have sensors with redundancy, then it helps you to perform the quality check more easily, and to make sure that the data is also correct, because you can start a comparison between the data collected by the two sensors at the same location. But obviously, the budget of Oklahoma, which is funded by the state of Oklahoma, is much, much higher than what TAHMO has. We do have a couple of redundant sensors in TAHMO as well, but it's just a handful of them at the moment. But to answer your question, we do calibrate our sensors as well, because even with expensive sensors, you still have to recalibrate. So, for example, in Oklahoma, what they do is they have a specific schedule where, whether the sensor is broken or still working correctly, they'll bring it to the lab and clean it up and recalibrate it and go back and deploy it. They don't wait until the sensor is broken before they do that. But in TAHMO, we have very limited budget. We do calibration of sensor, but not as frequently as Oklahoma does. So there's also a budget constraint here in TAHMO.
Yeah, she's saying, I'm not judging the quality of the sensor. I'm asking this because I have seen this done on air pollution. People construct local sensor, and then there is a need for recalibration. Actually, that was just a follow-up
Yeah,
message.
yeah, no, I did get your. I mean, I hope I got your question.
Yeah.
Yes, yes, we do recalibration very frequently.
Okay.
So I don't know if that answer. Yeah, definitely. Yeah, I mean, the sensors, the technique I'm discussing, even though in my work I mostly focus on precipitation. Yeah, it applies broadly to like other kinds of sensor as well. So thank you, Naomi.
Um. Okay. Uh. There's no question now online. I had a question about the clusters. You did some cluster size robust analysis, and then at the beginning, I when I saw the map for the TAHMO in Kenya, and I saw one point up there, or I mean farther from the others, I was wondering if there is no distance. You talked a little, said a little bit about it some minutes earlier, but is there no maximal distance where you're like physically you don't include it in the neighbors, that it will have no effect, or um, that
Yeah, that's a very good question. So right now in our experiment, we have a radius of 100 kilometers. So we have when a station is more than 100 kilometers away, we don't include it in the analysis. So yes,
okay.
we do have that. We have a maximum distance. So we assume that beyond 100 kilometers, basically you won't be able to draw any signal from the station that far. We do have so for example, this station, which according to this scale doesn't have any station around it, won't be able to do any quality control at all because there's no signal to be drawn from. And again, what I'm showing here is not the entirety of the Kenya network. I'm showing only 23 stations. In Kenya, there's a lot more than 23 stations. It's just that for the purpose of our experiment, we were looking for stations that have data in 2 complete years. So the map of Kenya has a lot more stations than this. But for the purpose of the experiments, for us to analyze the different methods we are comparing, we needed stations that have at least 1 year that we can use for training the models, and 1 year that we can use for testing. And for the models that satisfy that requirement, we were able to find only 23. But the network is much bigger than that.
Okay. Makes sense. And so TAHMO, as I understand, is an NGO, and is is TAHMO deploying its own sensor? I guess in every country, probably in Kenya, there's also some weather organism or state
Yeah,
uh,
yeah.
government. How do you collaborate with them, and do they have also kind of a sensor network in place, or how is the collaboration in terms?
Yeah. TAMO is not replacing, weather organizations in the country. It's more or less a collaboration where TAMO comes in with the expertise and the sensors, and then they collaborate with local government where the governments allow us to install the sensors, and in turn we share the data with them. So the data that is collected at the given location is shared with the government and the schools, in which, so for example, if we have a sensor at Polytechnique, I'll probably check, maybe we do, maybe we don't. And if we have a sensor at Polytechnique, and then we'll allow Ecole Polytechnique to have access to the data that is collected there freely. So that's the kind of collaboration. Like we install the devices and we take care of the maintenance and all of that, but you have access to the data that is collected. So that's the kind of collaboration we've been having so far. And even though I'm saying it like that, it's not that straightforward to get that collaboration going. With some of the bureaucracy and some of the governments and all of that political issues. And so that's how we are functioning.
So how is so how many countries already like TAHMO in, and are they present in Cameroon, or is there
Oh
any?
yeah, we do have stations in Cameroon, and probably five of them. I mean, last time I checked, it was probably five, and maybe it's more than that now.
Okay.
I yeah, we definitely do have stations in Cameroon. So um,
And how many countries already in, like, all in Africa, all over Africa in general?
I don't know the specific number of
Okay,
countries, but
okay.
my guess is like we have we have partnership with at least 30 countries right now.
Okay. Okay,
I don't
that's
know
the
the
map.
specific.
Okay. That's the
Yeah,
map.
I don't
Yeah.
know the specific number of countries, but
Okay.
my guess is
I
that probably more than
I
30
missed that
countries
map.
already.
Yeah. Sorry. I
No,
missed
no,
that.
you're good.
Yeah. Okay. So, um, there is also, about still the distance. I was wondering if you have seen a difference in terms of your deployment, or your models, com- with respect to the region, because a country like Cameroon, we are like, uh, the continent, like, the African miniature in terms of climate. Like in the northern part, it's like dry usually. Like you have 9 months, like, dry season, and maybe
Yeah.
only 3 months, and then some parts where like, the Buncha, where it's like rains almost every day. So I was wondering if you, in the regions where you have deployed, have you seen difference in how the models perform based on the regions or not, or
Oh
how?
yeah, that's a very good question. We did do some climate analysis where basically what we were looking at is like what is the climate zone in which the neighbors are. So basically for our prediction, we try to make this analysis where we are like, okay, we will select only the neighbors that belong to the same climate zone as the target station we are investigating. So, but unfortunately for the data set that we're using, you're very less likely to see any kind of effect in Oklahoma, for example, because of the nature of the network. Like I showed you, Oklahoma is mostly flat, and the climate zone is more or less the same, and there's not a wide difference. But it would be nice to do that when we have much cleaner data that allows us to get more than 23 stations in TAHMO. But for the experiment that we did, we didn't see any significant difference at all in the performance with the small set of station in Kenya.
Okay. There's a question from, say, do they collaborate with local startups? And then she said, with Hydro, as we plan to partner with TAHMO to install sensors for flood prediction, can you enlighten more on how to go about such a collaboration? I think Hydro as is a startup. Yeah, she said. Yeah.
Oh, we're definitely open for partnerships, right? So if you look on the TAMO website, you will find, I can't speak of the administrative side of things. I'm mostly like a researcher back door. And but definitely, I'm 100% certain that we have opportunities for collaboration for sure. So, and TAMO is really easy to reach. And I'm also willing to make some introduction if needed. So yeah, you should, ask them to check, the TAMO website, tamo.org, and there should be information there on how to collaborate in many ways. I know they have collaborated before with some startups. I believe it was either in Kenya or something, and they are still collaborating at the moment, where they give you basically, I think, access to the data and with some requirements in return. I believe that was like that. You give them credit for the product you're building, and some other sorts of agreement. I can't speak to that precisely, so I'm speculating based on my recollection of what I've heard before. So, but I'm happy to make some introduction if needed.
Cool. I think everyone who has the same question about collaboration have heard you clear and loud. Yeah, she said awesome. Thanks. Yeah, I think I've cleared the question on my side. I may have more still a question, but I think we've gone for 1 hour and 13 minutes. So I just give few seconds if anyone else online has have a have a question, additional question. Otherwise, we will thank Irené and close the session. Uh, uh, yeah. So no more questions. So thank you once more, Irené, for coming, for joining today. Thank you for sharing your work with us. It's kind of a very critical problem with first with the data, and then in the sense that it also applies to agriculture and climate change that actually affects Africa a lot these days. So thank you so much.
Yeah.
Yeah.
Thank you, Jonas, for hosting me. I would like first to apologize again for the bad connection. So, Washington, the West Coast of the US have been having a windstorm, in the last couple of days, and we were without power for the last 3 days, and it just came back yesterday. And so the internet is kind of like disconnecting and reconnecting because of power outage. So I apologize for those kind of like interruptions, and I hope you guys.
No worries. It was rather smooth compared to what I would have expected for such a disaster. So thank you, and see you all for some new editions sometime in the future.
Okay.
Bye bye.
Okay. Bye bye.